Good evening, dear students. So this video lecture will tackle Unit 6 of your module, which is all about evaporation. I'll be discussing a brief introduction on what boiling point elevation is, what is evaporator economy and capacity, the heat transfer in evaporators, and we'll do calculations involving single effect and multi-effect evaporator. So evaporation, one of the main methods used for the concentration of aqueous solutions, refers to the removal of solvent or water from a solution by boiling the solution or the liquor in a suitable vessel. We call it as an evaporator, and withdrawing the vapor, this one, the solvent. Now, if the solution contains dissolved solids, the resulting strong liquor may become either a saturated or a thick liquor concentrate so that crystals are deposited. And evaporation has three main uses in the food industry. First is pre-concentration. So one is pre-concentration of liquid prior to further processing by using either employing spray drying. Second is reduction, of course, of liquid to reduce its volume and thereby reducing packaging, storage, and transport cost. The third is to reduce water activity for preservation. For example, is the sweetened condensed milk. Now, evaporation is carried out by adding heat to the solution to vaporize the solvent. The heat is supplied principally to provide the latent heat of vaporization and by adapting methods for recovery of heat from the vapor, say using multiple effect evaporators, that the steam coming out from the first evaporator will be used to concentrate the solution in the second evaporator, and so on and so forth. Now, it has been possible to achieve great economy using this heat utilization. That's why in most industries utilize either multiple effect evaporation using uh, backward, forward, or mixed feeding. Okay. So the design of an evaporation unit requires the practical application of data on heat transfer to boiling liquids together with the realization of what happens to the liquid during concentration. Okay, let's talk about boiling point rise. I think in your colligative properties in Chem 11, you've encountered this already. When we say boiling point rise, it is a difference between the boiling point of a solution and the boiling point of the water or any solvent for that matter at the same pressure. So we know that the boiling point of a solution, of course, is higher than that of a pure solute at the same pressure. So why in this diagram, we could see that at the same pressure, the boiling point, the new boiling point of the solution, Ti, is greater than that of the pure solvent, T1. Okay, so as evaporation proceeds, the liquid concentration increases. Of course, so the boiling point rises. Uh, let's just make a brief review of your colligative properties. Of course, we know that some colligative properties would include the vapor pressure lowering. What else? Of course, the BPE or boiling point rise. You have the freezing point depression. And lastly is your osmotic pressure. Remember the formulas for vapor pressure lowering? It applies Rayleigh law. Your P1 is equals to X times P1 naught. BPR, delta TB is equal to I kBm, freezing point, delta TF I KFM, and of course, pi is equals to I. For the osmotic pressure, pi is equal to ICRT, or in some books, we use uh, IMRT. Okay, so we know that addition of solutes, say assuming these are solutes here in the solution, addition of these solutes basically would lower the vapor pressure. And we know that the boiling point of a liquid, normal boiling point of a liquid. See, assuming you have a liquid, its normal boiling point is actually the vapor pressure at which the vapor pressure of the liquid is equal to the standard pressure, which is 1 atm. So when we say that if I would get assuming I have here a liquid solution, its boiling point, TB, is actually the temperature at which the vapor pressure inside, the vapor pressure of the liquid, the vapor pressure VP of the liquid is actually equivalent to the vapor pressure of the surroundings. And for that matter, it's always 1 atm. Okay? So if we change the pressure from 1 atm of 1 atm, either lowering it or a higher pressure, the boiling point changes as well. Therefore, we would say that the boiling point is simply the temperature, okay, the temperature at which the vapor pressure of the solvent here equals the pressure of the surroundings. Take note of that. I would expect you've encountered that in your chemistry. So to repeat, the boiling point of any solvent is simply the temperature at which the vapor pressure, yung vapor pressure ni liquid, is equivalent to the vapor pressure of the surroundings, or we know that it's always 1 atm. That is why when your solvent, water, starts to boil, well, when it starts to boil, that is, the temperature is 100 degrees centigrade, we know that the vapor pressure it reaches at that temperature, we know that the vapor pressure of water is already reached a 1 atm pressure, which is equivalent to the vapor pressure of the surroundings. And of course, we would know that once this is reached, the molecules still cannot escape. Now, kailan nyo nakikita na may steam na lumalabas? That is when the temperature is hotter than 100 degrees centigrade. Okay? That is why we know that the steam is hotter than 100 degrees C. Now, the solute, let's talk about the solution. Once you have the solute, the solute molecules taking up position at the surface of the liquid would definitely depress the vapor pressure of the liquid. So once you have already the solutes in your solvent, the normal vapor pressure of the pure solvent will now be depressed. Now we also know that we have to raise the vapor pressure of the liquid in order, of course, to reach the boiling point. And it means you have to input more energy to reach the same vapor pressure. And input of more energy, assuming heat, would definitely be equivalent to an increase in boiling point temperature to obtain the same vapor pressure. Therefore, we know that adding a non-volatile solute to a solution raises the boiling point of that solution. So, for example, you have here the normal boiling, the temperature at which the boiling point of a solvent is assuming T1. At the same pressure, for me to be able to maintain that, uh, uh, to reach that boiling point, when I have already a solution, you have to increase the temperature to reach the normal vapor pressure in order to um, achieve a new boiling point. That's why when we say BPR, it's actually the difference between the boiling point of the solution minus the boiling point of the solvent. Okay, so there are three ways to evaluate BPR. One is, as I've mentioned a while back, using your colligative properties, wherein Of course, we know that for boiling point, right, it's delta TB is equals to I kbm. Know that your I is the Van 't Hoff factor, which is the number of particles into which the solute dissociates. Okay, and that M is your molality, and Kb is the molal boiling point constant, which is for this matter, this the 0.52 degrees C per mole is actually the Kb for water. Most of the books uses 0.51 to 1. So for easier recall, we either use 0.52 degrees C per molar. Okay. The second way to evaluate BPR is by using During's line found in figure 1911 of your Faust. Okay, let's say for example, if we are tasked to get the BPR of a 50% NaOH water solution with an evaporator pressure of 4.7 uh, psia, what we could do here is, of course, find first the corresponding temperature using a steam table. I'm sorry for that. So the corresponding temperature at 4.7 psia. So at the pressure of 4.7 psia, find the corresponding temperature using, of course, the steam table. And by that, that is roughly around, I don't know if I have a picture of the steam table here. There you go. Let's check for a while. So a vapor pressure of 4.7, assuming this time, it corresponds to 160 degrees Fahrenheit. Okay, let's go back to that. So if my temperature is equivalent to 160 degrees F using the During's line, so I would just project at 160 degrees F and at 50 weight percent. So where is that 50 weight percent? 95, 50. So this thing here. So you have to just project it up to the line of 50 and then get basically the corresponding BPR. So this is your boiling point. Okay, so that's how we evaluate BPR using your During's lines. But of course, note that this is only for NaOH water system. Sorry for that. Can you please? Okay. The third one is by using a nomograph, which is found in figure 11-23 of your handbook. So in here, we're tasked to get what is the BPR of a 45% NaOH solution at a solution temperature of 210. So you are given here, ito yung line, ito yung, the inner numbers are your BPR. The outer is your solution temperature. Now you're given 210 here. So this is 210 solution. All you need to do is, since you are given NaOH solution, project this 210 temperature to the middle of the small circle belonging to NaOH. So let me just get the ruler. So if I have that, I have already the 210, project it there. So it's this 210, direct, sorry, it should be on the uh, middle of the solute given. Okay, let's do that again. So you have here at 210 and NaOH. Project it here. And then find the 45% NaOH. This is the weight percent of the solute. So you have here 0.45. At this end, what you need to do is again project from this until it touches the 45% and then read the BPR. So it's someone around 60, 61 BPR. Okay, so that's how you do it. So from your reference temperature, project it to your corresponding solute, and then from corresponding solute to the end of this vertical line, project it to the weight percent, and then read your BPR. Okay, so that's just how easy it is. Okay, now let's talk about heat transfer in evaporators. Again, the usual, of course, is expressed as Q is equals to U A delta T. And your U here, of course, is the strong function of temperature difference between the streams. And there are resistances that, uh, to heat transfer in evaporators. One is the condensing film heat transfer coefficient on the steam side of the exchanger. Second is the boiling liquid film on the liquid side, again, of the heat exchanger. Third is the scale. Of course, even in other heat transfer topics that we have discussed, it's always scale and fouling can affect uh, heat transfer rate. So here, scale or fouling factors on both the inner and the outer walls bounding the heat transfer surfaces. But of course, in most evaporator calculations, this is deemed negligible. And third one is the thermal resistance on of the wall material. Okay, let's talk about evaporator calculations. Okay, let's just consider first uh, evaporator calculations using a single effect evaporator. Of course, as usual, the very first is your overall material balance. So if you just have a single effect evaporator, in is equal to, so inflow is equal to outflow. So the in is your feed plus your VO, your steam. Feed plus steam is equivalent to the solvent that vaporized or that evaporates plus the thick liquor and the condensate. So it's F plus VO is equal to E plus L plus VO. But of course, whatever the steam that comes in, it just goes out. That's why VO is being cancelled here, and you arrive at a formula for the OMB of an evaporator to be feed is equal to the vaporized liquid plus the thick liquor. Solute balance. The solute balance is simply FXF is equivalent to LXL because there are no solutes in the condensate, of course, and also in the um, solvent that vaporized. Okay, so it is just FXF is equal to LXL. Now let's talk about enthalpy balance. Enthalpy, you have VO, sorry for that. You have VO. Okay, let's just remove this one. Okay, so if you talk about enthalpy balance, you have VO times HS plus what's incoming FHF is equivalent to EHE plus VOHC plus LHL. It's just basically material balance. Okay. Now, if we talk about heat balance equation, where does this equation came from? So based on the reference time at the start of everything, of course, we know that everything is liquid. Okay. Now, when everything is liquid, so your T reference is T sub I. Okay. Ti. And that for the feed, sorry, okay. So for the feed, you have here liquid at Ti, which is also equivalent to liquid at Tf. So that you have FHF is actually equivalent to FCPF, CP of the liquid. This time it's Tf minus T sub I. Now the thick liquor here is actually liquid at T1, Ti, and liquid at, again, it's equivalent to liquid at TL. So that you have LHL is actually equivalent to LCPL, CP times the L. Of course, we know that your T sub I, so since T sub I is equivalent to your liquid at T1, so magiging 0. They are equivalent. So Ti minus Ti. So you get that LHL is actually equivalent to 0. Now the vapor, at this point, you have liquid at T, you have here. It is liquid at T sub I, and then it becomes still liquid at T1, and then vapor at T1 until it reaches vapor at T sub I. That's why you have here your EHE, that's a vapor liquid at Ti. EHE is equivalent to your E, as a liquid, Cp of water, Cp of your water, that's basically the steam, times T1. This is T1 minus Ti. So that's T1 minus T sub I plus vapor at T1. What's vapor at T1? E times lambda 1. Plus vapor at Ti, that is E Cp of the steam times Ti minus T sub 1. This is T1, so Ti minus T sub 1. Such that I could now have here, of course, we know Cp of water is equivalent to 1. So if I am to get here, since it's T1 minus Ti, I have, okay, let's just write it para mas, sorry for that, para mas malinaw. Let's rewrite the equation. Okay, following this one, liquid, for the vapor here, you have liquid at Ti, it becomes liquid at T1. This is actually, sorry for the penmanship, liquid at T sub 1, then it becomes vapor at T1, finally becoming vapor at Ti. So that if I have EHE is equivalent to your enthalpy balance equation there, is equivalent to liquid at T1. So that is your E Cp ni liquid water times T sub 1 minus Ti. T1 minus T sub I. Okay? Plus vapor at T1 is of course E lambda 1. If this is E lambda 1 plus vapor at Ti is E Cp of the steam, because it's already vapor. This time it's T sub I minus T sub 1. Okay? And so since we know that the Cp of water is basically equivalent to 1, Cp of steam is 0.45, you have a similarity of this equation. So that is E times 1. If I would exchange Ti to T1, I would definitely multiply it with a negative para lang maging pareho. So negative E times 1 times this time it would become Ti minus T sub 1. Just so it would be equivalent to the ECP of the steam plus E lambda 1 plus of course E CP of steam is 0.45. This time is T sub I minus T sub 1. Okay? And we know that this equation and this can be combined. So it's 0.45, negative 1 minus 0.45. So I would have, therefore, E, your EHE is equivalent now to E times your lambda 1 minus TI, T sub 1 minus T 1. And take note that this is equivalent to boiling point rise. That's why you came up with an equation that EHE is equivalent to E times lambda 1 minus 0.55 because I have negative 1 plus 0.45 of E, that is 0.55 BPR. Okay? Now, if you try to include that in your heat balance equation, Q therefore is equal to VO HS minus HC, this one, is equivalent to E times this, lambda 1 minus 0.55 BPR, that's for the vapor, plus your FCPF. Kasi yung LHL, this one is already equivalent to 0. So that's the steam condensate, your heat balance equation. The steam coming in is BOHS minus HC is equivalent to the vapor, E lambda 1.55 BPR, plus the feed, FCPF TF minus T1 or TI minus TF, plus LHL, which is 0. Okay, that's why you now have the equation for Q in this here. And lastly, of course, you have your heat transfer equation, which is equivalent to QATO minus TI. Take note that this one, the second equation, is for the general case for steam that is superheated at steam at TS, naging saturated at TO, then saturated liquid at TO, and then subcooled at T sub C. Okay? Now let's solve one simple problem for a single effect evaporator. So the problem states that a solution of organic colloids is to be concentrated from 20% to 65% solid in an evaporator. Saturated steam is available at 10 psia and the pressure in the evaporator is 4 inches mercury absolute. The feed enters at 60 degrees F, and then the feed enters at 60 degrees F. U is given as 300 BTU per hour feet square degrees F. The water evaporated amounts to 40,000 pound per hour. No BPR and given ka ng CPF. Let's find first surface area, second steam consumption, and third is economy. Okay, I've prepared an illustration for that problem. Okay, let's start. First is overall material balance. Feed is equal to E plus L. And I know I don't have the amount of the organic colored feed, but I know that E is 4,000 pound per hour. I don't even know also the thick liquor. But anyway, you just have to plot it. E is equal to 4,000, 40,000 pound per hour plus L. Let this be your equation 1. Second, you do the solute balance. It is FXF is equal to LXL. I don't know the feed, but I know that it contains 20% solute, so that's 0.20 is equivalent to L times a 65% concentrated solution. Let this be equation 2. Solve simultaneously equation 1 and 2. You'd get the feed to be around 57,777.8 pound per hour, and your L is 17,777.8 still pound per hour. Now next, I need to get, in order for me to get steam consumption, VO, because these are steam consumption, VO. I'll utilize HBE, heat balance equation. That is Q is equal to V sub O, the one that we uh, have a while back. Okay, so instead of 0.55 BPR, this is for SI, since we have English units, that's basically 2.303 BPR. So we plot Q is equal to VO, HS minus HC is equal to E times H1 minus 2.303 BPR plus F, you're given CP of the feed, T sub I minus temperature of the feed. Okay, or we could use that also as, which is equivalent to FCPF, TF minus T sub I plus VO lambda O. Latent heat is equivalent to here, equivalent to E lambda 1. Now, using your steam table, at 10 psi A, given ka 10 pound square inch, using steam table. At 10 psi A, your TO is roughly 193 degrees F. So I know that the temperature here now is equivalent to 193 degrees Fahrenheit. Your lambda O is around 982 BTU per pound mass degrees F. Okay. At 4 inches mercury absolute, which is, if you change that to PSIA, that is roughly equivalent to 1.96. At 1.96 PSIA, your T sub I is equivalent to 125 degrees F. This is also equivalent to T1. Why? Because we do not have boiling point rise as indicated in the given problem. Okay. So since that is equivalent to T1 is 125, you could get now your lambda 1, which is around 1023 BTU per pound mass degrees Fahrenheit. Okay, so since I know lambda 1, I know VO, I know CPF, I know the feed, I know the temperature, I'm now ready to get my VO. So that is Feed is 57,777.8 times, sorry, you have CPF equivalent to 0.93, TF minus TI, T ng feed is 60 degrees, T sub 1 is 125, TI 125 plus your VO, lambda O is 982, is equivalent to E, which is the 40,000 given, times the lambda 1 of 1,023. And easy peasy, you get VO to be around 45,000 to 6.75 pound per hour. Okay. And then you have here, so you know already that this is your V sub O, which is our steam consumption. Now we could utilize the equation Q is equal to UO AO delta T. It's basically equivalent to VO lambda O to get your area. And your area here, or AO, your AO basically is equivalent to 45,226, which is your given B sub O. So VO lambda O divided by UO delta T. So that is VO is 45,226.75 times lambda O is 982 all over UO and delta T. UO is given as 300, delta T is 193 minus 125. TO minus your T sub I. So that's 193 minus 125. And you get that to be around 2,177 feet squared. Okay, so that is your surface area of the evaporator. Okay, last is we need to find for the economy. Economy is given as E over VO, or that is your 40,000 over your 45,226.75, and you get your economy to be around 0.88. Okay, so it's just basically your evaporator calculation. It's more on just knowing the exact equation and doing material or heat balance. Okay, now let's go to multiple effect evaporator. So I think you have three different types of feed. You have a forward feeding, backward feeding, and some uses a mixed feeding. So what are the difference between the three? First is forward feeding is used for a hot feed. So this is actually the simplest, and so it is the most common form of feeding. The feed passes in the same direction. So the feed passes in the same direction as your steam, okay, or your vapor. So the first effect to the second effect to the third, and so on and so forth. So usually an extraction pump only is required, the final effect being operated, of course, at a very low pressure again. And with this arrangement, the viscosity of the processed liquor increases during passage through the plant, owing to both an increase in concentration and reduction in temperature. Because, say, assuming you have the hot feed here, you use this steam to evaporate some of it water, and then the one that coming through here, of course, you would know that the last feed would, of course, receive the lowest temperature. That's actually the disadvantage of a forward feed. Of course, high quality steam condenses in the first. So this one, the highest quality of steam condenses already at the first effect calandria. So if the initial feed is below its boiling point, some of the heat must be transferred and must be used for preheating. You have to need to preheat the feed stock. Okay. Now for we have also four equations. Uh, in the forward feeding, you have overall material balance. Again, parang katulad ng single effect that it is V sub O, the one entering steam, steam plus feed is equal to V sub 1 plus V2 plus V3 plus of course your L, your final, plus your V sub O na lumabas. Okay? Everything that enters is equivalent to the one that goes out. Therefore, if I say that if you say that your F is actually equivalent to V1 plus V2 plus V3 plus L, of course, the feed is equivalent to all the solvent that vaporizes in the first calandria, second, and third. That's your V1 plus V2 plus V3 plus the thick liquor that comes out. And you know that E is equivalent to V1 plus V2 plus V3. Thus, you have F is equal to E plus L. And again, we try to check on FXF solute balance. So your solute balance here, let's try to check the solute balance. So for solute balance, you have here, the one that is entering is FXF is equivalent to LXL. But that is also equivalent to F minus V1 times X1 and equivalent to F minus V1 minus V2 times X2. And the rest for the computation of your uh, heat balance equation and your for the first, second, and third effect is given by this. So if I have your EBE that is equivalent to, if I am to consider the first effect, this one, the first effect, I have F HF plus the one coming in VO times HS is equivalent to V1 times H1 plus F minus V1 times HF. So this thing, the condensate or coming in as the feed for the second, plus the VO times H sub C. So this is the EBE for your first effect. Now we go to the second effect. Take note, the one coming in for the second effect is the feed that goes out from the first going to the second, which is actually yung F minus V1, right? So you have here F minus V1, so ito yung papasok sa second, times HF minus V1, plus the vapor coming in, V1 times H1, is equivalent to F minus V1 V2 times HF of that plus, of course, your V1 H sub 1. Okay, and the V2 times H2, right? So the one coming in is F minus V1 plus V1 H sub 1 is equivalent to the 3 that goes out, the second calandria. You have F minus V1 HF, V1 H1, and your V2 H2. Okay? Now, how about the third effect? The one that goes out from the second is the one coming in for the third effect evaporator. So you have F minus V1 times HFV1 plus the, the steam coming in is V2H2 is equivalent to V3H3 plus V2H2 plus LHL. Okay, so it's as simple as that. Now, we talk about HBE. For your NaOH water system, so ganun lang, balancing lang din. VOHS minus HE, V1H1, F minus V1, and so on. So, uh, applying your equation for your BPR, so you finally get equation. I think this one is given in your module. Okay? And last but not the least is your HTE, which is constant regardless of the method of feeding. So this is all equivalent. Either you have a forward feeding, a backward feeding, and a mixed feeding. Okay, let's talk about backward feeding. So in here, yung kanina sa forward feeding, the steam comes in along with the feed, same direction. Here, in the backward feed, the feed comes through the last calandria and steam is on the first. So this is here the first, the second, and the third. So you have here the advantage is this is actually designed if you have a cold feed. Okay. So for backward feeding, dilute or cooler feed liquor emits the poorer quality steam since the steam and the liquor flows on the counter current. But an improved steam economy results. This is because the increase of viscosity is offset by the higher temperature encountered in the last. Yung last na condensate mo, the thick liquor, actually comes in contact with the highest um, the temperature for the steam. Okay, so that's why this is best used for your cold feed. Okay, so I think we are to the same. So same lang yung pagkuha ng mga equations either for forward feed or backward feed. The first step is you do it, OMB, second is solute balance, apply EBE, apply HBE, and so on and so forth. Okay. The best way to illustrate is by solving this problem. I think I have given this in your learning assessment, so -1 na dun sa learning assessment ninyo. Okay? So you are given, this one is a backward feed. Find the heat transfer area for each effect, assuming you are given an NaOH water solution given at the feed rate is 99,207 pound per hour, having a 10% solute and at 120 degrees Fahrenheit, and then leaving at 50% mass. You are given that your U1, U2, and U3 is equivalent to 500 BTU per hour, feet square degrees Fahrenheit. T3 is operated at 1.5 psi IA, and steam is available at 140 psi. All we need to do is find the heat transfer area for each of the effect given. Okay? Okay, let's do that step by step. Step 1. So we have here solute balance. So let's write step 1. We do solute balance. Why would I choose solute balance? Because I know already the feed rate. I could just easily get the thick liquor rate before solving for my overall material balance. So we do SB, solute balance, that is 0.50 of the L thick liquor is equivalent to 0.10. Okay. Let's write the equation. So I have LXL is equivalent to FXF. So I have L times 0.5 is equivalent to the feed, which is given as 99207 pound per hour times a 10% mass. Therefore, I could easily get my L, and that is equivalent to around 19,841.4 pound per hour. Now, step 2, I could use, before the step 2, I'll still use overall material balance. That is E is equivalent to the feed minus L. And that is 99207 minus L to be 19841.4, and that's basically around 79365.6. Take note that this E is actually equivalent to V1 plus V2 plus V sub 3. Okay, step 2. We know that uh, you are given 140 psia for the steam. I'd rather get TO and T sub 3 kasi given ako ng T3, given ako ng TO. Vapor pressure of the steam and the final vapor pressure at the third effect. So sorry for that. It's step 2. At 140 psia for the steam, I could get actually T sub O here. TO is equivalent using the steam table. You get that as around 352.974 degrees Fahrenheit. Using the still, of course, steam table. And next is at T3. I could now get T3 at 1.5 psia. Your T3 is given at around 115.349 degrees Fahrenheit. Okay, so you get T3, you know that already, and T sub O. Now we get the solute balance around effect 3. If I have the solute balance at effect 3, I would have F minus V3 times X3. So if I get the solute balance here, I would know that I would have F minus V3 times X3 is equivalent to FXF. This one, FXF. And I know already feed to be 99207. 99207 minus my V3 that I got a while back. If I would have E is equal to V1 plus V2 V3, and assume that your V1 from here, assume that from here your V1 is equivalent to V2 equivalent to V3. So that is 79365.6 divided by 3. That's roughly 26455.2 pound per hour. Take note, this is our first assumption that V1 is equivalent to V2 equivalent to V3. Okay, so if my V3 is 26455.2 times X3, which is unknown, I know FXF to be 99207 times 0.10. I could easily get my x sub 3, and that is roughly 0.136. Okay. Why would I need this? Because I could use your During's line to get your T3, your T123. Okay. This is at 115.349. Asan yung T3 natin kanina? Ito. It's 115. Sorry for that. It's 115.349. So at 115.349 degrees F and X3 of 0.136. Okay, you get your T3 by using your During's line, because the one given is for an NOH water solution. So we could get now the boiling point of solution T3 by projecting 115.349 here. So assuming I have 115, so 120, so halos nasa gitna. And a weight composition of 13.6, so just above your 10. Ang next na kasi is 20. So you need your bionic eye to get that value. So project it roughly here in between, and then project it on the ordinate. That's why you could get roughly a temperature of 125 degrees Fahrenheit. So if my T3 now is equivalent to 125 degrees Fahrenheit, I could use a solute balance at effect. So you have here, pardon for that. If I know already T3 by using your relationship for your BPR3, BPR3 would then be equivalent to 125. Okay, so 125, that's the temperature that we got a while back. So at 125, T3 minus yung T113. Okay, so that's 125. Ito, temperature of the solution. So BPR3 is 125 minus the 115.349. And BPR3 would then be equivalent to around 9.651 degrees F. Okay, now we could use solute balance at effect 2 to get furthermore the BPR, so that we could finally get a temperature distribution diagram for all the three effects. So using this effect 2, if I get the solute balance, again, it's F minus V2 minus V3 times X2 is equivalent to, ang pumasok is F minus V3 times the X3 that I've computed a while back. So that is 99207 minus, since V2 is equivalent to V3, 2 times 2645.2. This is multiplied by X2, which is the unknown. F minus V3 is 99207 minus 26455.2 times the computed X3, that is 0.136. I could now easily get X2, which is equivalent to 0.214. And use this equation. Note that you have a relationship that if I have BPR3 1 minus x3 all over x3 is equivalent to BPR2, 1 minus x2 over x2. I could now get your BPR2 since I know already a while back your BPR3, which is equivalent to 9.651, 1 minus 0.136 all over 0.136, equivalent to the unknown BPR2, 1 minus 0.214 all over 0.214. You get BPR2, which is roughly 16.690 degrees Fahrenheit. So same formula applies for me to get your BPR1. I could use BPR2 relationship. So I have BPR2, 1 minus x2 over x2 is equivalent to BPR1, 1 minus x1 all over x1. You know x1, of course, to be equivalent to 50%. Note that this one. Okay. So that I would have 16.693, 1 minus 0.214 all over 0.214 is equivalent to the known BPR1, 1 minus 0.5 all over 0.5. You get BPR1 to be 61.312 degrees Fahrenheit. And know that the summation of your delta T is actually equivalent to TO minus 3 T3, the initial for the steam minus the final temperature of the steam at the third calandria, which is actually equivalent minus the boiling point rise. So you get TO is 352.974 minus T3 is 115.349 minus the summation of all the BPRs, which is equivalent to BPR3 9.651 plus BPR2 16.693 plus BPR1 61.312, such that I could get the summation of delta T to be equivalent to 149.969 degrees F. Then, since I know already my summation of delta T, that is, you know for a fact that your delta T1 is equivalent to delta T2, equivalent to delta T3, or uh, can I use a space here? So I know already that delta T1 is equal to delta T2, delta T3, and that is equivalent to your summation of delta T multiplied by 1 over U all over 3 times 1 over U, or the 3 over 1 over U, since it's a summation, that is equivalent to 1 over U1, 1 over U2 plus 1 over U3, or para hindi kayo malito, it is 1 over U all over 1 over U1, 1 over U2 plus 1 over U sub 3. Since U1, U2, and U3 are all equivalent to the given 500, I could now get your delta T1, delta T2, and delta T3, which is equivalent to delta T2, delta T3, is equivalent to the summation of delta T, the 149, the one that we've computed a while back, 969, multiplied by 1 over 500 all over 3 times, since U1, U2, U3 are equivalent, 1 over 500. And you get delta T1 to be around 49.99 degrees F. Now, since I know already the delta T1, I could now use these values to plot a temperature distribution diagram. Note that your T sub O while back is 352.974, and that your delta T1 is 49.99. TO plus delta T1 is equivalent to your T sub I. Okay, so 352 minus 49.99, you get that at 302.984. And your BPR1, what's your BPR1 na? 61.312. So 302 minus BPR1, which is 61.312, you get T1 to be 241.672. And again, we know that your delta T2 and delta T3 are all the same. 241 minus 49.99, you get that. That's 191.682 to be your T2. And BPR2 is 16.693. So 191 minus 16.693 is equivalent to 174. Minus your delta T3 again of 49.99, you get 124. And from the 124.99 minus BPR3, which is 9.651, you arrive T3 to be 115.348, which is, note that this value is the T3 that we got a while back, 115.349. Oh, kulang lang siguro because of rounding off to get 115.348. Okay. Using the temperature distribution diagram, we're now ready to get from the steam table. So ito yung use why we need to get the plot the temperature distribution diagram for us to be able to get from the steam table ano ang values lahat ni enthalpy, HO, for the liquid, for the vapor, liquid, H1, H2, H3 to get your H sub 1. So these are all from steam table. Assuming, kanina I have, for example, okay. So at HO, we know that our TO, actually the one that we have a while back, TO, ano yung TO na natin from the start? TO is 352.974. Where is the 352.974 to get your enthalpy of the vapor here? Since my T sub O in the temperature distribution diagram is given as 352.974 from the steam table, you get, again, that's 352. So saan banda si 352? So it's in between 340 and 360 by doing interpolation for the value of the vapor, 1190 and 1194, to get your temperature, 352 point something, interpolate to get your H sub O. And by interpolation, you get 1193.725. And then your HO of the liquid is between 311 and 332. So these values, 311, 332, you get that H for the liquid to be around 324.98, and so on and so forth. By using your temperature for T1, 302, you get H1. For T2, you get these values, and so on and so forth. Okay? Until finally you get all the values. And then, using your effect 3 to get your HF at 120 degrees and 10, at effect 3, ito. Okay, given ka ng 120 and X of 10%, you could finally get H of F to be 79 BTU per pound mass. You also get H sub 2. Then you apply the formula for the EBE to be V2H2 minus H2 V3H3F minus V3. So that you come up with an equation in terms of V2 and V sub 3 and use this as your equation 1. Then again, use effect 2 to come up with another equation. And finally, you would know, diba, your equation 3 is the very first assumption that we have that your V1 is equal to V2 equal to V3. And then that value, if you add, that is equivalent to your E, diba? E is equal to V1 plus V2 plus V sub 3. Use that as your equation 3 to solve values for V1, V2, and V3. Why? For you to be able to check the assumption, the very first assumption that you have, that V1 is equal to V2 equals to V3. And obviously, they are not equal. So if they are not equal, the first time that you use these values to repeat everything. Ba? So for second trial, so this is using trial and error method. So kanina, we assume your V1 is equivalent to V2 equivalent to V3, which is 26. The value is 20, around 26, asan na yun? 26455.2. This time, they're not equal. You have individual values already of V1, V2, and V3. So again, repeat from here. Ito, mag-start ka ulit dyan. Since you know already the value of V3 from your new calculations, get X3, get T3, then the BPRs, get all the BPRs, make a new temperature distribution diagram. From steam table, you get all the values of this, and then using effect 3 and effect 2, use your solute balance in effect 3 and effect 2, and then you again solve for new values of V1, V2, and V3. Okay? So first, bumalik ulit tayo. We use again the formula F minus V3 X3, but this time ang V3 is 24094,135. This one. You get a new value of X3 to be 0.132. Use during to get your T3, get BPR3. Solute balance at effect 2 for you to get your X2. And by using your BPR, what do you call this? BPR formula to solve for your X2, X3, and finally your X sub 1. Okay, let's just say BPR3. For me, your BPR1 that you get, your new value is 9.151. 1 minus was X3, 0.132 all over 0.132 is equivalent to the new unknown BPR2, 1 minus 0.198 all over 0.198. You get a new value of BPR2 to be equivalent to 14.856 degrees Fahrenheit. Using this to get your BPR1, so that is 14.856, 1 minus 0.198 all over 0.198 equals BPR1 times 1 minus 0.5 for the feed, still for the feed all over 0.5, you get BPR1, which is roughly equivalent to 60.174. Now we know already BPRs, again, solve for delta T, which is equivalent to T sub O, 352.974 minus your T3 na 115.349 minus the summation of your BPR, BPR1, 60.174 plus 14.856 plus 9.151. And you get your summation of delta T to be equivalent to 153.44 degrees F. Then again, uh, using that delta T to be 153 to get your delta T1, delta 2, T2, delta T3, which is 153.444 times 1 over 500 divided by 3 times 1 over 500. You get that value to be 51.148. So since we arrive at that, let's do now a new um, what is temperature distribution diagram along with their enthalpy values. So at TO 352.974, you get your delta T1 to be equivalent to 51. This one is equivalent to delta T1, delta T2, delta T3. Ito yun, to. So we start again. TO is 352.974 minus 51.148 is 301.86. BPR1, 60.174, the one that we get here. Okay. 60.174. So 301 minus 60 is 241.652. Minus again your delta T2, you get 190. Minus your BPR2, 14.856, you get 175. Minus your delta T3, 51.148, you get 124. Minus 9.151. Still you get 115.349. Take note, hindi ito magbabago. Okay? And then, from steam table, you get the corresponding enthalpies. Compute for H1, H2, and H3. Then this one. And then, using effect 3 to get a new value, a new equation in terms of V3 and V2. Using effect 2, since alam niyo na lahat tong values ng mga enthalpies and latent heats. So you can arrive at another equation 2. And this time again, use V1 plus V2 plus V3 is equivalent to E, which is 79365.6. Solve the three equations simultaneously, and then you arrive at this values here, which is V1 is 30224.429, V2 2505.74, and 2408513. Now, if we will check these values through conducting another, so this is second trial. If we conduct again another trial, we will come up with such values that are very near these values. So it is because the change in your x1, x2, and x3, take note, ang change na nakuha natin for, where is that? X1, X2, to X1, that's X1 that we got a while back na. So X3, X2, and X1, which is 0.5, nearly changes. So negligible na yung change. Very negligible yung change that we have. So that's why if we conduct another third trial, halos pare-pareho. And that your BPR. Note that the BPR that we got from the first, 49.99. 61.312 for BPR1. Compare it with the second trial, nakuha natin 60.174. Very near yung values nila. That's why if you get another trial, halos pareho na. That's why we could say that these values that we got for V are actually reasonably correct. Now, since we know already your V1, V2, V3, you could use the formula U1A1 is equals to V O lambda O, or V1H1 plus LHL minus FV2V3 H sub 2 over U1A1 to get your A sub 1. Now, substituting the values, I could now get your A1 is equivalent to V sub 1, 30, 30224.429 times h of 1 from the same table that we got a while back, 1188. I think this is can be found from, hindi to nakasama dito. Yung h sub 1 na malaki. So 1188.3565 plus your L 19841.40 times yung H sub L 301.5 minus the F V2 V3 feed is 99207 minus V2 25055.754 minus V3 of 24085.417. This is multiplied by H sub 23, which is around 138.5. And everything divided by U1 delta T1, which is 500 times the delta T1 of 51.148. Finally, you get A sub 1 to be around 1367.227 feet squared. So same computation for your A2. We get at 1156 and A3 to be 952. Okay? So that's how you compute or calculate any parang. It's more actually on understanding what happens inside the evaporator, what are the balances that I need to know for you to be able to get or to solve problems on uh, evaporation. So in summary, evaporation process is used to concentrate a solution of a non-volatile solute in a volatile solvent, and usually the solvent that you use is water. Evaporator functions as heat exchangers, using again still the general heat transfer equation. Q is equal to UA delta T. Capacity was defined as amount of water vaporized per hour, and to determine this, the heat transfer through the heating surface must be known. Economy E over V sub O, and for multiple effects, water from one evaporator becomes the heating medium, diba? The one that we evaporate here, say this is Calandria 1, is the one that you used, sorry for that, you used in to heat in the succeeding evaporator. And for single evaporators, straightforward computations using either the material balance on solute and OMB and the enthalpy balances. But for multiple effect, we've proven that a trial and error calculation is required. Okay, so thank you very much. You are to submit your next learning assessment. Take note, dalawang simpleng problem na lang yun because I solved this as an example, yung problem number 3. So you are tasked to deliver, submit your learning assessment in evaporation by next Saturday. Okay, that's I think May 1. I don't know, is May 1 or April 30. Okay, so once again, thank you very much.